Assalamu alaikum. So welcome to lecture 20 of data mining tasks and techniques. So today we will continue with our discussion on clustering algorithms. So this would be our third lecture on clustering. So in the last lecture we had discussed the K-means algorithm in reasonable detail. So we will start from there today and then move on to some other partitional algorithms. And then from there, we'll move on to another category of algorithm, which is the hierarchical clustering algorithms. And I think that's pretty much for today. If we have time, we might even start algorithms that are based on density. So in other words, so we'll be discussing algorithms and their ideas in this lecture. All right. So are there any questions? Any questions? So uh, so So a couple of announcements, a few announcements. We are still, I think, uncertain regarding whether LUMS would open for on-campus as regular with regular classes. So, so, but as I mentioned in the last lecture, we still plan to take our quiz next Monday. So if RO decides that we cannot have that on campus, then we will have it online or in some other way, but it will be on Monday. So your next quiz would be on Monday, which is next Monday, April 6th, I guess. And the next assignment would be released either today or tomorrow. That will be on clustering and outlier analysis. And you also need to start work on your project. You need to decide your groups, and the project handout will be released also in a day or two. And the first task in that aspect would be deciding on a topic. And essentially, the topic is trying to find a recent work or recent paper in data science and data mining related to the topics that we studied in this course, and then try to re-implement it. So kind of re-evaluating or rerunning a already published work. So you can use the data that was already published. You can even use some of the code that was published. But the idea would be to evaluate, discuss, analyze the results that you get. So through this process, you go through the entire process of uh, understanding someone's work, implementing it, and evaluating it. So this is also a key step in research, but it's also important in the industry as well. So not just primarily research oriented, it is industry oriented as well. Okay, so these are some announcements. So any questions? All right. So in the last lecture, we had discussed the K-means algorithm, clustering algorithm. The K-means algorithm uses a clustering criterion or objective function. And this objective function, as you have written it here, is defined over all objects 1 to n. So n is the number of objects, and it's defined over all the clusters. So capital K is the number of clusters. So as such, this is called a global criterion. In other words, this criterion considers all the objects in the data set at once and tries to minimize this. Objective function is an error function or a cost function. It tries to minimize this. And it's also quite intuitive because what is it trying to minimize? It's trying to minimize the distance of every point from its respective mean. So if you minimize that, then you obviously have assigned the object to the correct cluster. Okay? So, and then that I that I've written there, that's basically indicator function. So that essentially says that we do not compute the distance of every object with every cluster mean, but only with the mean with which to which it has been assigned. So ik would be 1 if object xi belongs to cluster k. Otherwise it would be 0. So that summation में सिर्फ वही सम ऐड होगा, बाकी सम ऐड नहीं होंगे उस ऑब्जेक्ट का. ठीक है. And mk is the mean of the cluster ck. ठीक है. तो इस मैंने ये इक्वेशन इसलिए लिखी थी because again we need to start from here. There are some key points that need reiteration. एक तो ये है कि mean for example has to be computed. So it means that the cluster must contain objects that are all defined by numeric attributes, So you cannot find the mean of, for example, ordinal or so for nominal attributes or categorical attributes. Okay? So you need to have numeric attributes defining the objects so that you can compute the mean. And the mean is a point in space in general. So it not necessary that it actually represents an object. It might be a point in space. It may not be an exact object. Okay? So that's one thing that you need to keep in mind. The other thing is you have the distance function d. So d is the distance function or dissimilarity function. So this need to be known for k-means to run. Okay? You cannot run k-means if you only have pairwise dissimilarities available to you. So why is that? Anyone can think. I just mentioned the reason a second ago. Because you need a function to find the distance of every point with a mean. That mean may not be a point. So even if you have pairwise distances of all points in your data, you won't be able to find the distance of a point with any arbitrary point, which is not exactly an object in the data. Okay, so you need a function. So k-means requires that you need a mathematical function or that can give you the value between 2 points, the distance or dissimilarity between 2 points. In the original k-means, which is an old algorithm, this was often this Euclidean distance. So d is the Euclidean distance, and this is also the most common distance that is used. Euclidean distance, you all know what Euclidean distance is, but in the objective function sometimes, so d, so Euclidean distance is most common or popular. ठीक है? What's happening? Okay. So it's the most popular. And if you square this, so this is obviously you are taking the under root away from the Euclidean distance. So that error function then becomes, so E so then E basically becomes your sum of squared error. So which is identical actually. So if you square something, a monotonic function, आपका objective minimum वही होगा जहाँ पहले था. But it makes computation a bit easier because square root खत्म हो गया. So sometimes that error function, if you square it, is also called the sum of squared error. Okay? So that's another thing that you need to keep in mind. Of course, if you use Euclidean distance में every point and every other point का distance का square होता है, L2 norm है ये. So that often leads to issues with outliers. So in that case, you can use D as the Manhattan distance. So you can use the Manhattan distance. So that is also equivalent to the L1 norm. So this does not square the values. So in other words, so it's less prone to outliers and the influence of outliers. And of course, D can be used, cosine similarity is also commonly used. In that case, of course, similarity, then you'll have to maximize that error function. Okay? So cosine similarity is commonly used as well. So one other point that you can see from this equation, you need to know K. So you need to know K. And this is somewhat common for all partitional algorithms. So upfront, you need to know how many clusters exist in the data. So that is typically not very easy for real world problems. Okay? So, so how do you decide what is the best K? Uh, so the most common, there are two actually approaches, and of course, both of them are kind of not very accurate. One is, of course, use human judgment and knowledge. The human expert tells you, okay, this data set may have, let's say, 5 clusters or 10 clusters or 15 clusters. So let's say the human knows something about the data. Let's say you're clustering students, and you have a hunch that the students would be grouped among 4 groups, maybe roughly corresponding to their ranks, let's say freshman, junior, sophomore, and so on. तो इस तरह के इंट्यूशन की बेस पे आप के सेलेक्ट कर सकते हैं डिपेंडिंग ऑन योर डेटा. The other approach is a kind of automatic, or you can say a mathematical or objective approach. So, but it's still approximate. So in this case, essentially you plot E vs K. ठीक है? So ये कर्व प्लॉट करें एरर विद K. तो मतलब in other words, you run your algorithm multiple times with different Ks. आपने एक दफा K को 4 रखा, दूसरी दफा 5 रखा, 6 रखा, 7 रखा, 8 रखा, 10, 15, 20. You get a plot for E. So in general, if you increase K, E would decrease. So why? Because जितने आपके क्लस्टर ज्यादा होंगे, क्लस्टर छोटे होंगे, एरर कम होता जाएगा. Because average distance of each point from the cluster centered would decrease. So in other words, if you increase K, E would monotonically decrease. Okay? And technically, let's say if E becomes if K becomes equal to N, E will become 0. Okay? Her object would become its own mean, or object distance with mean would become 0. ठीक है? तो so इसमें ये है कि इससे फिर हमको किस तरह पता चल सकता है. So there's a hunch. Let me try to draw that figure. Let me first open this. So if you plot this figure, this E versus E on the y-axis and K on the x-axis, तो आपके पास इस तरह का कोई कर्व आएगा. So you notice that you might get some kinks. Kinks का मतलब ये है कि you might see some points at which there is a change in the slope of this curve. So slope would always be decreasing because, as I said, monotonically decreasing. What is E and K? So E is the error objective function जो आपका था, उसकी value है. K is the number of clusters, capital K. So y-axis पे आपके पास E है, x-axis पे आपके पास number of clusters है. You cluster the data using different Ks. And the problem that we want to address is कि हमने देखना है कि इस data set के natural clusters कितने हैं. Because obviously upfront we don't really know. ठीक है? So unless you have domain knowledge. So actually there are just two ways of guessing that. One is domain knowledge, the other is some heuristics approach using this curve. So what I'm drawing is the curve between E and K. So this curve would decrease, but if you might see some kinks. Kinks का मतलब क्या है? जहाँ slopes change हो रही हैं. So maybe यहाँ change हो रही है, फिर यहाँ change हो रही है, फिर यहाँ change हो रही है. So these are potential points of K at which that would represent the natural number of clusters. So if you have just one distinct kink in your कर्व, तो आपको पता है कि ये काइंड ऑफ is close to the natural number of clusters in a data set. ठीक है, but if there are many, then obviously you are stuck again to decide which one to choose. And if you don't see any distinctive kink in the slope, then again you are stuck. ठीक है? So this is one way of deciding K. So any questions here? Okay. Okay. ठीक है? So the point K at which you notice a kink in this curve might be a good estimate for the number of clusters. Okay. So so that was a refresher of K-means. उसमें other properties भी हैं. We already discussed those last time. You tend to get spherical clusters. You tend to get clusters that are compact and of almost of same size. It's and it's a relatively efficient algorithm. K is needed upfront, and so on. So now let's move on to another variation of the partitional algorithm or the K-means algorithm, which is called the K-Medoids. ठीक है? So overall algorithm का process वही है K-means वाला. Process क्या था K-means का? You select K points, initial seeds, you find the so those initial seeds are the initial means. You assign every point to the nearest mean, and then again compute the new mean. So in this case, the prototype, so cluster proto is an object. It's an actual object in the data. It's not the mean. Okay? In K-means, it is a mean. Mean is a mathematical point that may not be an actual object. But in K-Medoids, it's an object. And the medoid naam वहीं से आ रहा है, median object, the middle object. ठीक है ना? So the prototype, each cluster is defined by the centrally located or the median object in the cluster, not a mean. ठीक है? तो इसमें so why would we want to do that? So एक तो रीजन जैसे मैंने पीछे बताया था, you need to know the function d. So you don't need to know d explicitly. If you just have pairwise dissimilarities between objects, then you can still apply K-Medoids. Because आपके सारे distances between points ही होंगे, between objects ही होंगे. Unlike in K-means, आपके सारे distances between points नहीं होते. They are between points and a mean that may not be actual object. ठीक है? So that's one advantage. The second advantage is that since you don't need to compute a mean, so it can be applied to non-numeric data as well. ठीक है? So it can be applied to non-numeric data as well. So non-numeric data का आप मतलब of course it has to be ordinal, median central located data निकालना है. but sorry, not necessarily ordinal. As long as you have pairwise distances, you can still find the middle object. बट न्यूमेरिक होना जरूरी नहीं है कि आप मीन किस तरह निकालते हैं, सम करें, डिवाइड बाय टू करें, वो नहीं जरूरी नहीं है. इट मे बी कैटेगोरिकल डेटा as long as you have distances between them. So that's, I think, a good advantage. Uh, Another advantage that usually arises because we are not using this Euclidean distance, although in K-means you can use other distances as well, but usually we use Euclidean distance. So it's less prone to outliers. And of course, another way to reason about this is since you are choosing the middle object as the centroid or prototype of the cluster, that is less prone to outliers. जी, so we are coming to that. So हमने वो central object ढूंढना किस तरह है. So that's actually the main difference between this algorithm and the previous algorithm, K-means algorithm. So just hold on a little bit second. ठीक है, so it's less prone to outlier because central object is not likely to be disturbed by an outlier. Central object is like a median. Median आपका less prone to outliers होता है, while mean is more prone to outliers. So these are some of the positives for this algorithm, but as we will see, आपको centroid ढूंढने में computational extra करनी पड़ेगी, so it's computationally more expensive. So what is the idea here? So हमने start उसी तरह करना है. So initially select K objects as medoids. ठीक है, ये तो वही है. Then you repeat. ठीक है, assign each object to nearest medoid. ठीक है. Of course, this is based on the pairwise distances that you have. You may not necessarily need an objective function, or sorry, a distance function, a dissimilarity function. Okay? So once you have assigned every object to the nearest medoid, you need to find the new medoid. So this is where you need to do an extra loop. ठीक है, वहां आपको previously you need to do just one computation, mean निकालना है. यहाँ आपने एक नया medoid ढूंढना है, which is, as we'll see, would take an extra loop और वो एक extra complexity डाल देता है. And rest of the algorithm is same. So and repeat basically until convergence. ठीक है. So how do you find the new medoid? So let me give you a simple example. Of course ये iterative है. So let's say मैं cluster C1 की बात कर रहा हूँ. ठीक है. क्या cluster की भी जरूरत नहीं है. So let's say we are talking about medoid 1, and let's say this is some object x, let's say 3. Remember, medoid would be an actual object. So M1 का मतलब ये है कि ये for cluster 1 है. So this is the current medoid, and you want to find if there is a new medoid that would be better. So we use the property of a median or the middle object to find the new medoid. So anyone can guess what that property could be? An important property of a middle object? So an object would be centrally located if the distances of all other objects from that object is a minimum. ठीक है. So let's say आपके पास एक cluster है, यूं करके ये I'm showing with my hands. I hope you can see this. इस क्लस्टर में let's say एक सेंटर में कोई पॉइंट आप मीडियन लेते हैं तो सारों के डिस्टेंस थोड़े होंगे. ठीक है. और let's say एक इधर पॉइंट ले लूं मैं एज द मीडियन, सारों के डिस्टेंसेस ज्यादा होंगे. The sum of the distance would be much higher for a point that is not in the center. and for a point that is in the center, distance would be a minimum. ठीक है? So we are talking about cluster 1 and currently उसको x3 मिला हुआ है. So we will check all the other points excluding the other m's. So in other words, you have to check n minus k other objects, replace it with x3 and see if the cost error decreases or not. ठीक है? So ठीक है? So if E increases, obviously that is not a candidate. मतलब obviously वो जब increase हो रहा है इसका मतलब वो central तो है ही नहीं. E3 was better, X3 was better. But if it decreases, and there may be many that causes to decrease, we'll choose the one that has the least error. So in other words, let me say कि हमारे पास जो candidate है X10 है, इसका error मेरे पास E10 कलर से आ रहा है, let's say 15 आ रहा है, और एक मेरे पास एक X11 है, इसका मेरे पास 11 लेट्स से आ रहा है 13 है, और लेट्स से X15 है, और इसका एरर 15 जो है लेट्स से मेरे पास 18 आ रहा है. ठीक है? तो सबसे थोड़ा एरर किसके साथ आ रहा है? ठीक है? तो X11 का एरर 13 आ रहा है. तो इसका मतलब है जब X3 को हम करेंगे, बाय द वे X3 के साथ एरर हमेशा ज़्यादा ही होगा, वो मैंने लिखा नहीं है. सो X3 का भी लिख दूँ. X3 जो होगा ना, दिस विल प्रॉब्ली लेट्स से 20. ठीक है? सो इफ यू रिप्लेस X3 विद X11, our error will decrease, and this is the minimum among all the objects that we have tried that causes a decrease in error. इसका मतलब we will replace X3 with X11. So this is our new medoid for cluster 1. So M1 आपके पास अब हो जाएगा X11. ठीक है? So we'll do this for all the other M's. So ये एक एक्स्ट्रा लूप चल रहा है ओवर एंटायर डेटा सेट. तो इसकी कॉम्प्लेक्सिटी फिर ऑब्वियसली इंक्रीज हो जाएगी. आइट्रेशन तो उस तरह ही रहेंगे. टी इज द नंबर ऑफ आइट्रेशन, वी टॉक्ड अबाउट दिस लास्ट टाइम. एन इज द नंबर ऑफ ऑब्जेक्ट्स. ठीक है? ठीक है? एंड देन वी हैड के इन नॉर्मल के मीन्स. टी एन के ये हमारा नॉर्मल के मीन्स था, हर बिकॉज के वाज फिक्स्ड. ठीक है? अब यहाँ हमारे पास एक और एन माइनस के आ जाएगा. So obviously this is n square. So this becomes an n square algorithm, not an n algorithm. वह दो n इसके अंदर आ रहे हैं. Since k is much smaller, n is much larger. So इसकी computational complexity ज़्यादा है. And as we will see later on in the other algorithms, there are hardly any other algorithm in clustering that does as well as k-means. That is why k-means is considered most popular and most efficient. सारे जितने भी क्लस्टरिंग एल्गोरिथम दे आर ऑलमोस्ट ऑलवेज n स्क्वायर या मैक्सिमम n log n. ठीक है? उससे बेहतर नहीं है. ठीक है? So the question again to repeat is, why would one use K-Medoids if we don't have a distance function defined for our data set, but we do have pairwise distances? We want our results to be more robust to outliers. Okay? And finally, if our data set is not purely numeric, such that its mean cannot be computed. Okay. So in general, in practice, K-Medoids is considered a robust algorithm in practice. मतलब it does find good clusters. Okay. So if you have time or you have capacity, तो K-means के साथ K-Medoids भी चला लेना चाहिए, just to make sure कि आपकी clustering decent आ रही है comparison के लिए. ओके. अब इसके अलावा थोड़े से और वेरिएशंस भी हैं के मीन्स के, दे आर लेस कॉमन. वन इज द के मीडियन. सो दिस इज essentially very similar to K-Medoid, but median, as you know, is maybe a point, not an actual data. ठीक है. So median would be a point, not an actual data. The only benefit that you will get in using this is कि आपके पास outlier का impact कम होगा, and so that's the only benefit. You still need to have a distance function, and you still need to have a data set that for which a mean, for which median can be computed. So median compute करना पड़ेगा. Of course, this would be efficient because n square नहीं होगा, ये n पे वापस आ जाएगा. Because median आप direct एक computation से कर सकते हैं. Of course, that depends on the data, of course. ठीक है. So, but as I said, K-Medoids is kind of more common. इसी तरह का एक और वेरिएशन है, वो K-modes है. So this is primarily meant for categorical data. कि आपके पास डेटा बेस प्योरली कैटेगोरिकल है, ए बी सी डी है एंड अदर कैटेगरीज हैं, एंड दिस इज बेस्ड ऑन frequencies. So the mode is the most frequent combination for an attribute. ठीक है. So for example, let's say आपके पास एक डेटा सेट है. Let's say I'm talking about a particular cluster C1. तीन एट्रीब्यूट्स हैं, ए और बी. मतलब थ्री एट्रीब्यूट्स हैं. पहले की वैल्यू ए है, दूसरे की ए है, तीसरे की बी है, और फिर बी है और ए है और बी है, और फिर बी है और ए है, और लेट्स से ए है. सो व्हाट वुड बी द मोड फॉर दिस? सो पहले का मोस्ट फ्रीक्वेंट अकरिंग वैल्यू इज बी. सो मोड वुड बी बी. दूसरे का मोस्ट फ्रीक्वेंट क्या है? तो दूसरे का ए है. तो तीसरे का बी है. A and B. So this would be the mode, and this would be considered as the prototype for this cluster. So एक cluster में तीन objects थे, all of them described by three categorical attributes. So you have found the cluster prototype, which is the mode. अब आपके पास जो भी कह लेंगे function है, you can use that function to find the similarity between objects and this mode. ठीक है. So of course इसकी भी efficiency n ही होगी, n square नहीं होगी, as long as you have a efficient way to compute the mode. ठीक है. The rest of the properties would be similar to K-means, मतलब spherical ही होगा. Spherical की property कहाँ से आती है? Because we are representing each cluster by just one point, one prototype, और बाकी सारे distances उससे हैं. तो spherical ही cluster ढूंढेगा, compact clusters ही होंगे, because we are minimizing an objective function, almost all of the same size, because एक size छोटा हो एक बड़ा होगा, error ज़्यादा हो जाएगा. It will make sure कि all clusters are smaller and of the same size, error थोड़ा होगा, and so on. तो बाकी प्रॉपर्टीज वही हैं. ठीक है. सो इन टर्म्स ऑफ क्लस्टरिंग एक और इम्पॉर्टेंट वैलिडेशन का एस्पेक्ट होता है, बट वैलिडेशन थोड़ा सा मैं होल्ड ऑन कर लूंगा until we discuss a few more algorithms. So validation itself would take couple of lectures, but since आपकी assignment में validation भी होगी, तो I wanted to स्टार्ट अर्ली, बट एक वैलिडेशन तो आपकी ये एरर फंक्शन से ही हो सकती है जो मैंने अभी आपको बताया। ठीक है, सो एरर फंक्शन कैन बी यूज फॉर वैलिडेशन एज वेल। ओके, सो लेट्स मूव ऑन। ऑफ कोर्स इसमें बाकी सारी चीजें आप कर सकते हैं। यू कैन क्लस्टर ए सैंपल ऑफ द डेटा to make a quick assessment. If your data set is very large, एक random sample ले लें और उस पर k-means चला लें, so you'll get a good idea of the clusters in the data. And other tricks that are common to all of data science, वो आप कर सकते हैं यहाँ भी। अच्छा, so let's move on to hierarchical clustering. So this is a category or type of clustering algorithms. तो इसमें भी अंदर काफी algorithms होंगे. So partitional algorithms were also a type of algorithms. ठीक है, अब इसके अंदर भी कई एल्गोरिथम्स होंगे। इन पार्टिशनल वी स्टडीड द के मीन्स प्राइमरीली, और उसकी फिर वेरिएशंस, मोस्ट इंपॉर्टेंटली के मेडॉइड्स और फिर के मीडियंस एंड के मोड्स। अब इसमें क्या है, हायरार्किकल क्लस्टरिंग में, एज द नेम सजेस्ट, वी आर clustering the data, you can say, in steps. ठीक है, so we are not doing it directly. In partitional algorithm, you had an objective function that was a global objective function that directly found k clusters. In this case, we do not specify k. So k is not specified upfront. Instead, we run the algorithm through multiple steps which are hierarchical. हम पहले data set को, let's say if you are doing it, there are actually two ways, agglomerative कर सकते हैं, divisive कर सकते हैं। ज़्यादा common agglomerative है, agglomerative, दूसरे divisive. So agglomerative में क्या होता है, you start with each cluster, each object being its own cluster, meaning that आपके start में you have n clusters, k is equal to n, every object is its own cluster, and then in the first step you merge the two clusters, in this case two objects that are most similar. ठीक है, so first step में आपके पास दो points, या if they are equal distances तो maybe more than 2 points can be combined in one cluster. तो अब आपके पास एक cluster हो गया और बाकी सारे clusters रहेंगे, and then you repeat this iteratively until you decide to stop. Of course, if you do not stop, at the end of the day all objects would cluster into one big cluster, which is actually useless, your entire data set. ठीक है, so ये एक hierarchy बनती है, hierarchy of clustering. At the start you have, at the bottom you can say, you have n clusters. At the next level you maybe have some number n minus some number less than that cluster, then some other less than the others, until you get one cluster, which of course is useless. So now you don't need to specify k, and then you can decide by visualization or by some other technique, like say validation, which number of clusters you want to keep. ठीक है, so that's the idea here. ठीक है, so divisive उल्टा चलेगा, you start with one, all the data as one cluster, then divide it. So let me just take a simple example, 1D, आगे हम एक्चुअली देखेंगे भी इसको किस तरह करना है. So let's say मेरे पास x1 है, x2 है, x3 है, x4 है. So initially, so this is my first step. So मेरे पास k is equal to 4 है. Every object is its own cluster. ठीक है, so at the first step I'm going upwards. ये bottom था. At the first step, let's say मैं कहता हूँ कि x1 and x3 are the most similar. So you need to have a similarity function or some way of quantifying the similarity between objects. So I'll combine x1 and x3 into one cluster. And then I will be left with x2 and x4. So हमारे पास अब k कितने हो गए? 3 हो गए. The first cluster is x1, x3, the second cluster is x2, and the third cluster is x4. ठीक है? So we do the next step. Again, we try to find the two clusters that are most similar. So maybe let's say x1, x3 उस तरह ही रहते हैं और ये दो मिल जाते हैं x2 और x4. Obviously आप k आपके पास यहाँ 2 हो गया. ठीक है? And obviously the final is of course useless. So x1, x2, x3 and x4. So k is equal to 1. ठीक है? So आप step wise number of clusters decrease कर रहे हैं by merging the most similar clusters. ठीक है? So it's that explains in a better way. Okay, so where do we stop? So that's a very good question. So at each step, you probably have to do a validation step. ठीक है? So validation जैसे मैंने कहा आप आगे study करेंगे in more detail as well. Intrinsic, extrinsic दोनों validations हो सकती हैं. Yeah, alternatively, as a data scientist yourself, you look at the clusters that you have obtained at each step. If you are satisfied at a particular level, then you can stop there and not go any further. Or maybe you can generate a few levels and then compare them and then decide which one to choose. Okay? So obviously k is equal to 1 is trivial and k is equal to n is also trivial and that are useless. We are only interested in those that are in between and usually those that are close to, so that are much less than n. ठीक है? अब you understand the process now. ठीक है? आपको of course इसी process से हम जरा complexity decide कर लेते हैं. So process आपको समझ आ गया. ठीक है? So at every step you need to decide which two objects are the most similar. ठीक है? एक तो ये है कि let's say in the worst case हमने so in other words, so let's say at each step you need to compare every object with every other object. ठीक है? For example, let's say जो पहला level था उसमें आपने every object with every other object compare करना पड़ना था आपको. ठीक है? So that would be what? So in general that would be n square. ठीक है? And then of course इसकी एक height भी है. Height usually of course would not be all n. If it is all n, of course ये n cube हो जाएगा. But usually we will go on to a few more steps जितने हमको चाहिए and then we'll stop. So that number of height you can say some level t. ठीक है? So t is the number of steps. ठीक है? So in general, this is an n square algorithm. It's much more expensive than k-means and sometimes even more expensive than K-Medoids. ठीक है? But इसका benefit ये है कि this is it does not take k as an input, and as a data scientist, you can visualize various k's or validate various k's and decide where to stop. So actually, this types of algorithm are also very good for initial clustering. So these algos are also very good yeah, preferred for initial clustering. ठीक है? So interactive iterative way में as a data scientist आप data को explore कर सकते हैं and decide कि data में clusters कैसे आ रहे हैं. ओके अब इसमें कुछ दो तीन इंपॉर्टेंट चीजें दैट वी विल नीड टू डिस्कस. एक तो ये है कि आई सेड दैट एट एवरी स्टेप we need to decide which two clusters to merge. So we need to have a merging criterion. कोर्स एक स्टॉपिंग क्राइटेरियन भी है, जो आपका क्वेश्चन था पहले। स्टॉपिंग क्राइटेरिया ऑफ कोर्स वैलिडेशन से ही डिसाइड होगा, आइदर बाय ह्यूमन जजमेंट और बाय सम ऑटोमेटिक वैलिडेशन, कि आपने कहाँ रुकना है, किस के पे रुकना है। ठीक है। सो मर्जिंग क्राइटेरियन is the important aspect here. So we need to have a way of deciding which two clusters to merge at every step. अब इसमें different techniques हैं. They all of them are very simple, but कुछ छोटे मोटे pros and cons हैं सारों के. So let me write them down first and then we will discuss them. And a couple of them do have names that are kind of not very intuitive. So the first one is called a single link. Okay. So let me write them down first. Then we have the complete link, and then we have the average link, and then we also have the what is known as centroidal link. And then actually there's another merge criterion which is not link or distance based, but that's based on variance. That's called the Ward's method या criterion. ठीक है. So these are some of the merging criterions that are used in practice. So what are we actually trying to decide here? We're actually trying to decide what is the dissimilarity between a cluster Ci and a cluster Cj. तो ये हम क्वांटिफाई करना चाह रहे हैं. ठीक है. Not necessarily object xi and object xa. Of course, in the start, एक cluster एक object ही होगा, तो ये it should kind of naturally कह लें कि boil down to that extreme as well. But in general, C1, Ci and Cj would be clusters that contain more than one objects. So we want to quantify this. अब इसमें जैसे मैंने कहा था कि सिंगल लिंक क्या चीज है, let me write it. So single link is the minimum distance between objects in Ci and Cj. In other words, this is the shortest link between the two clusters. The shortest link between the two clusters is the minimum distance between the objects in Cui and Cj. So let me write the other one as well, and then we'll maybe show you a figure. So next was complete link. So this is actually the max distance between objects in Ci and Cj. So as I said, ये names very intuitive नहीं है. The single link, of course, यहाँ भी एक, if you look at it in terms of a graph, this is still a single link, but this is a link between the two furthest objects in the two clusters. So let's say एक ये cluster आपका इधर है, एक cluster इधर है. Single link would be the nearest 2 points, or complete link with the furthest 2 points. Obviously, this is a measure. आपने decide फिर ये करना, if you have selected this measure, you decide you merge those two clusters that have the minimum complete link. And complete length itself is defined by the maximum distance between objects in those two clusters. So both of these techniques are influenced by outliers because they talk about one object at a time in one cluster and one object in the other cluster. The single link is the nearest two objects. So that tends to give you clusters that are kind of elongated, even though if they may be not very close, but they may have 2 points that are very close. While कंप्लीट लिंक से वो फर्दर पॉइंट्स देख रहे हैं तो दे काइंड ऑफ गिव यू कॉम्पैक्ट क्लस्टर्स। तो दो दूर पॉइंट्स दो क्लस्टर्स में जो सबसे करीब है उनको कंबाइन करता है। ठीक है, सो दीज आर two techniques, and then average link, as the name suggests, is the average distance between objects in C, I, and Cj. So this is less prone to outlier, but of course you need more computation. आपको total number of points in Ci and total number of points in Cj आपको process करने पड़ेंगे, pair wise distances निकालेंगे and divided by the total number of distances. ठीक है, so average link. So this is the average link, and then we have, as I said, the centroidal link. As the name suggests, this is the distance between centroid of Ci and C. So this is actually also a single link, but this is a link between the center points of cluster I and some cluster J. So in single points are, but these points are, let's say, more robust to outliers because ये central points हैं. But of course, to do this, you need to compute the central point for each object. ठीक है? So these are, if you ask me in terms of popularity, generally single link or average link ज़्यादा commonly use होते हैं, but they do have their issues. जैसे single link मैंने कहा था कि let me just show you a diagram here. Uh, okay. This. So basically आपके पास let's say दो clusters हैं, एक ये है और एक ये है. Centroidal link would be this, sorry, the single link would be this, जो nearest distance है. और ऑफ कोर्स आपका कंप्लीट लिंक है, ये एक ऑब्जेक्ट है, ये ऑब्जेक्ट कंप्लीट जो फर्दस्ट जो डिस्टेंस है वो है. सेंट्रोइडल ऑफ कोर्स दोनों के जो सेंटर्स होंगे, एक ये सेंटर है, इसका सेंटर है, सेंट्रोइडल डिस्टेंस वुड बी दैट. ठीक है, एंड ऑफ कोर्स एवरेज के लिए यू हैव टू कंप्यूट ऑल पेयर वाइज डिस्टेंसेस बिटवीन ऑब्जेक्ट्स इन C1 एंड C2 एंड देन टेक द एवरेज. ठीक है, तो सिंगल लिंक जैसे मैंने कहा था, सिंस लेट्स से आपके पास एक क्लस्टर यूं लंबा से इधर फैला हुआ है और एक यूं फैला हुआ है, ये सिंस ये दो पॉइंट्स क्लोज हैं इन दोनों को जोड़ देगा वो. ठीक है, बट जो आपका कंप्लीट लिंक है, लेट्स से एक ये यूं फैला हुआ है और एक यूं फैला हुआ है, इन दोनों के दरमियान डिस्टेंस बहुत ज्यादा होगा, तो ये जुड़ेंगे नहीं, मे बी यहाँ ये दो क्लस्टर ये जुड़ जाएंगे बिकॉज इनका डिस्टेंस कम होगा. ठीक है, एवरेज एज आई सेड इज बैलेंस्ड बट कंप्यूटेशनली स्लाइटली मोर एक्सपेंसिव, और सेंट्रोइडल डिस्टेंस इज आल्सो लेस प्रोन टू आउटलायर्स, तो वो भी यूज कर सकते हैं. ओके, अच्छा, वार्ड क्राइटेरियन है और मेथड. दिस इज बेस्ड ऑन variance. So in other words, we'll join those two clusters that will cause the least increase in variance. ठीक है. So since variance needs to be computed, so it can be only be applied to numeric data. ठीक है. The previous techniques थे वो mostly can be applied to other types of data as well, but variance can only be applied to numeric data. But this method in general is a bit more robust to noise, and it will give you better clusters. इसका जो फॉर्मूला है so for example the increase in variance is given by a formula. Let's say मैं इसको कह देता हूँ I C I डेल्टा भी कह सकते हैं, इंक्रीज है, ये चेंज है, C J. Of course we won't go into the derivation of this formula. So CI CJ का जो increase in variance हो रहा है, if you merge them, वो it's given by this formula. I hope ये formula से double check कर लूँगा बाद में. I think I may miss something. N1 N2 is the number of objects in N1 and C1. Sorry, CI और CJ था. ठीक है. Ni and J divided by their sum, Ni plus Nj, then multiplied by the Euclidean distance, D कर लेते हैं, but D is the Euclidean distance between the mean of I and the mean of J. So D is the Euclidean distance. ठीक है. So this formula gives you the increase. तो आपने वो दो क्लस्टर्स मर्ज करने हैं that causes the least increase. ठीक है. So you compute C1 C2 के साथ, C1 C3 के साथ, C1 C4 के साथ, C2 C3 के साथ, C2 C4 के साथ, जिसका सबसे थोड़ा इंक्रीज हो रहा है, those are the two clusters that you merge at that step. और फॉर्मूला ये है. So you need to know the center of each cluster and you need to know the number of points in each cluster. So since we need to compute the center, so this is only applicable to numeric data, mean point. So it's applicable to numeric data only. Okay. Any questions? Acha. Another aspect of hierarchical algorithms. So we have discussed the aspect of merging criterion. So we have discussed 4-5 merging criterions. We also discussed the procedure. We start with all objects being one clusters, their own clusters, and then you merge step by step. इसमें एक और important aspect है which is distinguishes from partitional algorithm is you have a local merge decision. ठीक है. So in other words, no global objective function. As in a partitional algorithm. ठीक है. आपने at each step you decide which two objects are the most likely to be merged and you merge them. Once you have merged those two objects will never be unmerged, or those two clusters will never be unmerged. मतलब एक आपने डिसीजन जब कर लिया, that decision cannot be reversed. तो बैक ट्रैकिंग as such नहीं है, although in algorithmic sense आप कर भी सकते हैं, but in almost all hierarchical clustering algorithm वो नहीं होती. ठीक है. So जब बैक ट्रैकिंग नहीं होगी तो obviously आपका optimality of the entire data compromise होगी. While in K-means या उस तरह के algorithms में एक objective function है जो पूरे डेटा के ऊपर जाता है और वो ऑब्जेक्टिव ओवर द एंटायर डेटा को मेंटेन करने की कोशिश करता है। ठीक है। सो इसका कॉन्सिक्वेंस क्या है? सो ऑब्वियसली you may not get the optimal clustering through hierarchical algorithm if you compare it with partitional algorithms. ठीक है, because there is no global objective function. Local merge decisions आपके optimal हैं, but from one step to the next step you don't make a decision that reverses the previous one. So for example, जैसे पीछे हमने example देखा था x1 वो x3 आपने merge कर दिया, तो आपके पास उसके पास था x2 और x4 था। ठीक है, जब x1 x3 आपने merge किया, they will always remain in the same cluster. ऊपर जाए जैसे भी जाएंगे they will always be in the same cluster. ठीक है, मे बी x1 x3 के साथ x2 मर्ज हो गया या x1 x3 के साथ x4 मर्ज हो गया, बट x1 x3 हमेशा एक में ही रहेंगे। इसको हम इस तरह भी कहते हैं, एक टर्मिनोलॉजी यूज होती है, कहते हैं देयर इज नो आइटरेटिव relocation of objects in hierarchical algorithms, while in partitional algorithms iterative relocation is possible. Of course that's done globally. आपके पास ऑब्जेक्ट्स एक क्लस्टर से दूसरे क्लस्टर पे मूव हो सकते हैं, बट इन हायरार्किकल क्लस्टरिंग जब आपने एक ऑब्जेक्ट एक क्लस्टर में डाल दिया वो हमेशा उसी में ही रहेगा। ठीक है। ऑलराइट, सो other characteristics of hierarchical algorithms would be dependent on how you define the prototype. तो प्रोटोटाइप लेट्स से आपने उसके सेंट्रॉइड से डिफाइन किया हुआ है, तो and you're using distances, so you tend to get convex uh, clusters, but not necessarily spherical. जैसे मैंने डायग्राम भी बनाई थी, आपका एक क्लस्टर यूं लंबा भी हो सकता है, कन्वेक्स तो है पर जरूरी नहीं है स्फेरिकल है। while K means prefers spherical clusters in space. ठीक है, unless of course if you use centroidal distance as your measure, centroidal distance करेंगे तो फिर kind of similar to K means की शेप आएगी spherical, but if single link कर रहे हैं आप, complete link कर रहे हैं या even average link कर रहे हैं, तो it's not necessary कि आपके पास purely spherical आएंगे। they may be they would be convex but not necessarily spherical. Okay, and of course computational complexity इसकी कम है with K means. इसके advantages of course ये हैं कि it is iterative, interactive, good for initial clustering, uh, and you have the flexibility of applying this to numeric data, to non-numeric data, and so on. एक फिगर है वो दिखा देता हूँ। So for small data sets, you can represent your hierarchical clustering through a figure that is called a dendrogram. तो ये एक किस्म की स्ट्रेट लाइंस, वर्टिकल एंड हॉरिजॉन्टल लाइंस की फिगर होती है। तो of course this is only convenient if your data set is relatively small. बड़े data sets के लिए I think this is only academic purpose के लिए है, but since it is mentioned in the book and may be used in some visualizations, So I'm mentioning this. तो so essentially इसमें क्या है कि of course this is a hierarchy. आपके पास at the start all objects are their own cluster. If you merge two objects, वो objects दो जाके ऊपर एक horizontal line से जुड़ जाते हैं. तो वो पता वहां से पता चलता है कि दो ऑब्जेक्ट एक क्लस्टर में आ गए एंड देन यू कंटिन्यू इन दिस फैशन. तो इस तरह की जो ट्री बनता है दिस इज कॉल्ड ए डेंड्रोग्राम. ठीक है. ओके. So there is another. So let me mention one divisive algorithm. So what is known as bisecting. So bisecting K means या K-Medoids भी हो सकता है या कोई और भी हो सकता है. So algo. So this is actually a divisive hierarchical. Okay. Hierarchical algorithm, but it's also an hybrid algorithm because it includes hierarchy as well as the K-means algorithm. ठीक है. तो इसमें आइडिया क्या है? वेरी सिंपल. सो आपके पास इनिशियल डेटा सेट है डी. ठीक है. सो यू अप्लाई के मीन्स यू स्टार्ट विथ के इज इक्वल टू 2. ठीक है. तो यू डिवाइड द डेटा इनटू 2. तो आपके पास दो क्लस्टर्स आ गए. ठीक है. एंड देन यू रिपीट फॉर ईच ऑफ दोज क्लस्टर्स दिस बाइनरी डिवीजन. तो आपके पास एक ट्री सा आ जाएगा. ठीक है. ऊपर एक क्लस्टर है, एक ब्रांच में एक उसकी क्लस्टर है, दूसरे में दूसरी क्लास. इस ब्रांच को फिर दो में डिवाइड कर दिया, इसको फिर दो में डिवाइड कर दिया, मतलब चार आ गए आपके पास. इसको फिर दो में कर लिया, इसको फिर दो में कर दिया, इसको दो में कर दिया, तो आपके पास 8 हो गए हैं. सो ऑन. ठीक है. सो दैट्स हाउ इट वर्क्स. ठीक है. देन फॉर ईच क्लस्टर आर डिवाइड फर्दर. ठीक है. सो इन अदर वर्ड्स इसमें फिर वही आपके पास हायरार्की आ रही है बट नाउ डिविजिव है. और आपको के सेट नहीं करना पड़ रहा, बट वी आर डिवाइडिंग दोज यूजिंग के मीन्स विच इज जनरली ए बेटर क्राइटेरियम बिकॉज इज बेस्ड ऑन एन ऑब्जेक्टिव फंक्शन. बट हायरार्की आपकी फिर भी आ रही है. और जब आपने एक डिवीजन कर दी, लेट्स से आपने इनिशियल डेटा को ये दो क्लस्टर में कट कर दिया, अब ये वाला क्लस्टर और ये वाला क्लस्टर इंडिपेंडेंट है, इसको आपने फिर के मीन इसको लगाया, इसको इंडिपेंडेंटली के मीन इसको लगाया, तो फुल ग्लोबल फिर अप्लाई नहीं हो रहा. ठीक है. सो इसमें वो के का इशू आप इन ए वे हैंडल कर रहे हैं. यू डोंट नीड टू नो के अप फ्रंट. आप हायरार्की जनरेट कर सकते हैं. टू सम एक्सटेंट आप जो जो मर्जिंग क्राइटेरिया था या डिविजिव क्राइटेरिया इज बेस्ड ऑन ऑब्जेक्टिव फंक्शन, इट्स गोइंग टू बी मच मोर रोबस्ट देन द प्रीवियस केस. ठीक है. सो दिस इज ऑल्सो क्वाइट कॉमनली यूज इन प्रैक्टिस. So I will briefly also talk about an algorithm called Birch. This is again a but hybrid hierarchical partitional algorithm, and it's hybrid. And also one of the characteristics an online algorithm. Online का मतलब ये है कि it can cluster data that is not all available at once. Meaning that आपके पास data stream है, एक point आया, फिर दूसरा point आया, फिर तीसरा point आया. It can cluster as the data comes in. ठीक है. So again थोड़ा सा इन एल्गोरिथम पे हम बहुत ज़्यादा डिटेल नहीं जाएंगे बिकॉज They are very specialized algorithms applicable or useful in specialized applications. तो टाइम भी खत्म हो रहा है। एक तो ये है कि आई माइट इंट्रोड्यूस दिस और आई कैन इंट्रोड्यूस डीबी स्कैन, सो आई थिंक आई शुड स्टार्ट विद दिस, लिख लिया मैंने। सो इसमें आइडिया क्या है? इसमें जो की आइडिया है वो एक डेटा स्ट्रक्चर का है, विच वी कॉल a CF vector, which means clustering feature vector. ठीक है? So in other words, we represent a cluster not by all the objects in that cluster, but by a efficient data structure that contains some key statistics of that cluster. कुछ stats उसके रख लेते हैं. And since I mentioned stats, so this algorithm is applicable to numeric data only. It cannot be applied to categorical data or even to ordinal data. It has to be pure numeric data. ठीक है? And what is a CF vector? So CF vector, let's say एक cluster का है, it is a vector of three things: n number of objects in the cluster, the linear sum of all the objects in the cluster, and the squared sum of all objects in the cluster. So ये तीन चीजें हमने हर cluster की compute करनी है, and then we can make decisions based on these alone. We don't need all the points. ठीक है? So something like synopsis या sketch. I don't know if you guys have studied stream algorithms or not, online या stream algorithms. तो ये उसका एक representation है which you can then update as new data objects come in. ठीक है? So let me just take an example. Let's say CF1. Let me, okay. 2D data ले लेता हूँ, 2 and 2 and 3 and 3. ठीक है? So this is, let's say, our cluster 1. इसका CF क्या होगा? How many objects do we have? We have 2 objects, right? So N2 हो गया. And what is the linear sum? हर एट्रीब्यूट का सम कर लेना. 2 + 3 5 हो गया, और फिर 2 + 3 5 हो गया. अब स्क्वायर्ड सम, हर एट्रीब्यूट वैल्यू को स्क्वायर कर लेना और फिर सम कर लेना. तो 2 + 2, 2 × 2 4, 3 + 3 9, 4 + 9 is 13, और दूसरा भी 13 है. So this would be the CF vector for this data set. So this cluster. So by the way, from a purely statistics point, so इसमें आपके पास moments आ रहे हैं, 0th moment, first moment and second moment. ठीक है? स्क्वायर की वैल्यूज भी आ रही हैं, लीनियर की भी आ रही हैं, and then of course the number of objects. So given this stats, you can find various things about the cluster. उसका for example centroid निकाल सकते हैं, उसका diameter निकाल सकते हैं, so on. So this makes computations easier, and then also finding how to input objects into clusters easier. Okay, I'll just mention one other thing that we discuss this in the next class. So let's say आपके पास एक और कोई cluster है CF2. उसमें let's say 3 है, or let's say, I don't know, I'll just take some random numbers, 5 and 8, and let's say 20 and 35. If you merge cluster 1 and cluster 2, the new CS is simply the sum of these two clusters. So if C1 and C2 are merged, the merged CF is simply CF1 plus CF2. So this is a property, and you can verify this very easily. कि आपने जब ये दो क्लस्टर्स मर्ज कर दिए तो इनका नया CF जो होगा वो n को आप सम कर लेंगे, ls को भी सम कर लेंगे, ss को भी सम कर लेंगे. So this would be the new CF. तो आई थिंक आउट ऑफ टाइम, सो इसी को थोड़ा सा हम नेक्स्ट टाइम डिस्कस करेंगे. इसका एक ट्री बनता है, वो ट्री को हम बहुत ज़्यादा डिटेल में नहीं देखेंगे, बट ये जो कोर आइडिया इसको एक्सपैंड करके देन वी मूव ऑन टू डेंसिटी बेस्ड क्लस्टरिंग. ठीक है. So for your reading, you should read your textbook, chapter 8. And also clustering is pretty well described in the other book, the Introduction to Data Mining book. उसका मेरे ख्याल से chapter 7 है या उसका भी 8 है. और that chapter by the way is available online, freely available है. So Intro to DM की book का clustering chapter is available online. नहीं आता, I can also upload it. So this is also describes the chapter in pretty good detail. In particular, the cluster validation is described very well in this book. So, and of course, you can use your own textbook as well. उसमें chapter 8 है. So data mining concepts and techniques में chapter 8 है. ठीक है. ठीक है. So any questions? Any questions? So this was the 20th lecture. I think we have 4 weeks after this still left. So I think 29 lectures तक जाएंगे. And I do plan to have take all those lectures. थोड़ा सा content है हमारे पास cover करना. So let's see. So as I said before, quiz आपका अगले Monday को ही है. वो modality हम decide कर लेंगे based on what is decided by LUMS. So if you guys can come on campus, that would be great. But otherwise, फिर देखते हैं क्या करना है. ठीक है. So okay, so